We are Group 18 and we present our implementation of KinectFusion. KinectFusion is a work presented in 2011 by Newcomb et al., where they presented a method for real-time mapping of indoor scenes. Our implementation builds a pyramid in order to do a cost-of-fine post estimation. This post is used to update our volumetric scene representation, which is later raycasted to obtain a surface and align future frames. For each depth frame, we apply bilateral filter in order to construct a vertex map and a normal map. Here you can see an example of a normal map with and without having applied the bilateral filter. The pyramid has 3 levels and each one of these levels contains a vertex map and a normal map. For post estimation, we first compute correspondences using projective data association. This means given a pixel, we access the vertex map and the normal map of the model. We project it to the previous camera coordinate system. We're using the inverse of the camera intrinsics, we map it to the current image frame. Then we access vertex map and the normal map at this pixel to obtain a point and a normal. We then compare them in the global coordinate system to measure their distance and the angle of their normals. If it's under some thresholds, we consider them a correspondence. These are some correspondences produced by our method. With these correspondences, we compute point-to-plane terms. These terms are linearized, as we can assume that the transformation between two frames will be small given that the characteristic of the sensor. We then compute this linear system using of dimensions number of correspondences by 6. We solve this least squares problem using SVD. This is solved in a cost-to-fine manner, meaning that we start in the lowest level, assuming that the current camera is the same as the previous one. We compute some increment performing ICP. We forward this increment to the upper levels until we obtain the estimated pose for the current frame.
After computing the new camera pose, we want to update our voxel grid representation of the scene by integrating the new depth frame into the sine distance function representation of the world. We go through our voxels and we project them back to the camera coordinates. Then we project them back to the image. Then we check if they have valid depth values and if they are in the camera frustum or if they are close enough to the surface. If they pass all the checks, we update their distance values using a weighted average fashion, and in the end we have the representation of the scene in our grid in our voxels. After updating our voxel grid, we want to extract a dense representation of the scene from it. So in order to do that, we shoot rays from the camera through each pixel in the image plane into the voxel grid. Then we march along these rays and we compute zero crossings. Whenever we encounter a zero crossing, we know that we have passed through a surface point. So we find the intersection and take that point as a vertex in the surface point. Then, since we also store the color information in our grid, we can incorporate it into our generated surface representation and have more visually appealing results. We can also cast rays to the grid from different viewpoints. For example, in this scene, while the camera was seeing this, we can generate this normal map and the color representation of the surface, but we can also have an imaginary camera in another viewpoint and generate surfaces like this.